Casual pose here. Hi, I'm Sandy Maguire. This is Existentialization. What is it good for? A talk by Sandy Maguire. If you want to follow along, the slides are online. If you don't, that's okay, because the slides are also here. So the talk is essentially like, what's some trickery we can do in the type system in Haskell. I had some motivating examples at the beginning and then kind of lost track of it by the end. So please just ask questions. We got unlimited time. So that's my little preface here. So the problem I originally started with is we want to be able to like automatically generate quick check properties for like instances we write. So like for example, if you write an instance of monad, you might be able to like prove automatically that it is a monad. It follows all the rules. So there are packages that can do this, but you have to like explicitly say, I want you to write me a quick check instance for this thing. So you say, here's the instance I want, and it'll generate tests for you. But that's like boring. Who's time for that? And so the idea is, why doesn't it discover all of the monad instances I've ever written and then prove that all of them are in fact monads? That was the original thing. We're not actually going to get to that, unfortunately. But that was the original problem I had solved when Matt asked me to do a talk. And so I was like, I'll do a talk on that. So we can talk about that later if anyone's interested. But first, we could say we're going to start with like a really dumb, simple example. And the simple example is that we're JavaScript programmers and we absolutely hate types. And so we want to just like stick whatever we want into a list. And you can't do that in Haskell. I hope this is legible in the back. But it's like we have a list of 1, 2, 3, and they're all integers, and that's fine. Things like a list of true, and that's fine. But we can't say we have a list of 1 and true because those things are different types. That's a type error. And then that's cool, right? The thing is, like JavaScript can do this. It's like if we say Haskell is such a great language, like shouldn't it be able to do all these cool things too? And so this actually turns out to be completely useless, but it is in fact a thing we can do, and it's a good kind of segue into these techniques. So it turns out Haskell is not as shit a language as some might say, and we can write this any type here. So we need to turn on gaddits, which are generalized algebraic data types, which essentially just let you write out the type of a constructor as you construct it. And so I can say I have a type called any, which has a constructor called any that can take some value of type A, and it's going to give me back a type of any. And so this thing is like a container, right? You can stick anything into it you want. But the problem is like we kind of forget what type it used to have. But the good news is we can now stick these things into a list. Well, actually, that's not. I've gotten ahead of myself. So I can say like I can stick true into an any and I get back an any. And I can put like show as some function into an any and I get back an any. And so we can say that this A here is now existential. Because we know that it exists, but we don't know anything else about it. Cool. And so the first question you might ask is like, what happens if we try to take it out, right? Because you can just pattern match on that thing, and we can say, oh, I've got an A here, I'm going to return it. And does anyone guess what happens here? Great participation, everybody. And we get this fucking gnarly error here. Could not match expected type T with actual type A because type variable A would escape the scope. This rigid Skolem type variable is bound by a pattern constructor with any for all A to any. All right. And this turns out to be an error you're going to see a bunch doing this technique until you get like pretty familiar with this stuff. And the question is like, why does this happen, right? So if we wanted to write like the actual type on this function, we'd say f is a type that takes any to A, right? But that's kind of short form for like this for all A here, right? And so what we're saying here is you give me an any and I'll give you back any type that you want. I'll give you back the type you're asking for. So if like this were used in the context of bool, that A kind of gets unified as bool. And so then I got a function that says I got any to bool, right? But most of the time, the thing inside of that any is not going to be a bool or an int or like whatever thing you actually want it to be coming out of. And so that's the problem here. And so what it's saying is you have a type and you're saying it's this thing, but it's not. Or at least I can't prove that it is, and so I'm not going to let you take it out. And so that's what a rigid Skolem variable is. It's existentially quantified, and then you're trying to remove it out of that existential quantification. at which point like it's not even a thing that you can even talk about, just syntactically you can, and so they need a weird error message for it. So this kind of solves the thing we were first talking about, or at least just now. We can say we can make a list that can contain all sorts of values, right? We can put 5 and bool and show into a list, and it's fine. This type checks. You can't do anything with it except like take the length of it, but that's great. We can do this thing that we set out to do, so that's great. But just because that isn't useful doesn't mean the technique isn't useful. So we're going to talk about iterators, like in Python or more objective languages, where you have like you want to be able to produce a series of values, and those values are probably going to be different as you pull them out, which implies that there's some sort of like state in there, right? And we don't really care what the state is as long as we can pull out those values. So our first attempt might be something like this, right? We have an iterator of type S and A, where S is the internal state, and A is like the values I'm pulling out. And so I can take the value in state and put it into next, and that'll give me this tuple of like a value in a new state, right? So I've written a state monad here. And then if you just kind of keep running this thing, you'll just get a series of A's out. And that's kind of cool, right? But the problem is the internal state isn't internal anymore, right? We have this S variable that's like propagated to anyone who might want to use this code. And that means like you can't stick 2 of these iterators in the same list if they have different internal state because they have different types. So the idea is like we can existentialize that thing, right? The whole point is we don't want that variable to leak outside. So I've done the same thing here, except now S doesn't show up here, right? So now it's existential, it doesn't come out. But we can say still we have some iter state of S and iter next of S. And so great, it doesn't leak out of the type signature anymore. And that's kind of cool. So we can actually write the function that will pull out these iterators just by wrapping this stuff. And so we say like, we're just going to bind iter next to get next. We're going to call it with the state that we have inside of our iterator, and then construct this pair of the thing we got out and the iterator with the new state inside of it in the same pumping function. This is kind of neat, right? Because we're using that existential type. There is an S in here that's being used, even though it doesn't explicitly show up anymore. And so that's kind of what I'm trying to say here is like, we think of these things as like sharing some existential type here. And even though we don't know what that type is externally, GHC is still smart enough to know inside of this definition that these things are referring to the same type. And so all this stuff type checks, even though if you were to like try and run it by hand in GHCI, it wouldn't, because those types would get lost. Is that everyone following so far? Cool. I'm going to power through then. So we're going to talk about something different now, kind of along the same lines. So we have this thing called a dict, short for dictionary, and it takes a thing that is a constraint. It's not a type, right? So it has some type parameter, but this thing is not a type. It is, in fact, a constraint. And the constructor for it says, as long as I have a proof of that constraint, I can construct a dictionary of that constraint. This thing is like isomorphic to unit, except that it's packing information at the type level. The C is not existential. That's why I'm saying it's something different. But it's kind of interesting anyway. And so we can say that the dict of C is a proof that I have a C. It's like a proof of C that I can pass around at the value level. And so I can say I have a dict whose type is dict of enum bool, right? Because bool is an enum, then this is constructible. Likewise, that int is showable, so I can construct that. But equality is not defined for functions in Haskell. And so I can't get a dict of equality for int to int. Right? So this thing will just like not type check, and it'll just fail. And that's kind of neat. So I'm kicking things under the table here. So like you might be asking why. Who cares, right? But the thing is now we can pass our constraints along as values rather than kind of implicitly in the type system. So I can write a show function here, which is like maybe show it, right? And so this thing is defined for any A. And like if you can prove that it's showable, then I'll use that show. And if you don't, then I'll just say like, I don't know how to show it. So the way that this works is if you pattern match on this dictionary, that constraint that you kind of packed into there comes into scope. And so this show is the same as this show constraint here. We just get that by pattern matching. Otherwise, nothing, I don't have to show, right? And so just to prove it works, I can show true, and I can not show like the function flip.
Is this using any extensions to Haskell, or is it?
This is like used pretty much everywhere once you get into like spooky stuff. Like Edcomet has a constraints package. You need to turn on the constraint kinds extension, which gives constraint as a kind that you can talk about. Yeah. So we don't care too much about dicts, but we do care about this kind of idea of like packing a constraint into here. And so we can actually do this same thing to like make our any list a little more usable, a little more like valuable. And so what we can do is we can pack a proof of show as when we construct these things. So now we can't construct a list of anything, but we can construct a list of anything that's showable, right? And then what I can do is I can show that thing, right? Because that's obviously the only thing I can do with a list of things that I only know is showable. But at least it's a little more valuable, right? Now I can pack heterogeneous types into this thing and then show them later. So I write a little show list function, right? So it unpacks the show, that pulls this show into scope, and then I can write that as a string. And then so I can say my list, I'm going to make a showable list. These things are all different types. And I can show that thing, and I get packed this stuff, right? Great. So that's kind of cool. But something we can't do, which looks similar at first, is this thing here. We can say, I want to pack an equality proof in here, and I got an A, an equatable. And then I should be able to like equate two of these things, right? Some people are shaking their head, and that is correct. Because why, right? The question is, I guess it's because we have these two existential variables now. We got A and a B, and we have no proof that they're the same. And so we can't actually compare these things because this thing won't type check. Lame. But that's okay. So just like some things you can and can't do with this, right? It's kind of worth keeping track of like what type variables are happening. So you might be wondering, like, more generally, what is the fucking use of this stuff? And the answer is, if you can provide an eliminator for these things, you can use them. And so an eliminator is a function that can like take your existential value and then do something regardless of the type inside of it and produce some value. So as long as you can do that for any type, then you can do it for whatever type is inside of that, right? And so you kind of, in general, this thing has this shape. I take some existential, and I take some type variable that I don't know what it is. I could choose that being the author of the function, not the caller of the function. And you can give me a function that you want to return an R, and I will return that R for you. It's a little wild, but we'll see a couple examples. So a dumb example is like if we just ignore the existential variable entirely, right? If we just return back true, we don't care what thing is inside of this, so we can always produce a Boolean, right? So it is, theoretically possible to produce values regardless of the type. In general, kind of this function is not going to have that shape. You want to replace this for all A thing with the actual definition of the existential. And so if I have showable here, I replace that thing with for all A, show A to R. And so this is saying, as long for any type A that you have, we know that it's showable, and I want you to produce an R. So that thing might be show, right? This function. I want whatever is inside of that, I want you to produce a string for me. Or we could like use that and get the length of that string. Or we could kind of do any computation that requires this show, or doesn't even require it, and we can just ignore that entirely. But this is capabilities that we're providing to the callers of this function. Another example is this iterator thing, right? And so we can say, so this is kind of the definition of the iterator, and if you squint, it looks the same as that. These are the things in there. And so for any S now, right, which is the thing we're existential over, as long as, if you know what these things are, we want an R. And that thing could be like pull at the A, that could be like try to find the fixed point. The thing is, like, as long as you don't return this S, you can do whatever you want in here with these things. Because if you return the S, you've got this rigid Skolem problem. But yeah, I like this title. It's not a very useful slide. I think we talked about it though. So let's use this for like realsies. And let's say we want to make a server. Maybe not like a HTTP server or something, but just like something that will respond to requests and it'll reply with something and maybe do some I/O in the meantime. The idea is like we want to be able to make a bunch of different endpoints for this thing, and each of the endpoints can take different types as arguments and return different types as results. So in order to do this, let's say we're going to use byte strings as our medium, right? So we're going to just say, my type A is encodable if I can turn it into a byte string and come back out of a byte string. In reality, this can probably fail, but I didn't want to do it. And so we just assume that we have encodables for like every type we'd ever want that's like reasonable to serialize. And I can kind of existentialize a function in the server, right? So if I know if my input is encodable and my output is encodable, I have some function that from A to I/O of B, right? And then I'm going to existentialize both the A and the B into this thing. So now some handler is a container that like holds some function that I know runs an I/O and can be converted to and from byte strings on either end. Cool. So if we assume we have some like receive function that takes like the endpoint I want and some payload, and I can also send back a response, I guess this should actually be a byte string to I/O unit. Whoops, that's what happens when you put these together really quickly. But let's say I have a server, right? And I want to say I've got a list of endpoints and a handler for that endpoint. And I want to run this thing. So kind of in a loop, what I do is I receive the endpoint and the payload I want. Then I'm going to look up my endpoint in the list of endpoints I have. And that's going to give me some handler if it exists. So in here, if I destructure this thing, that pulls in the encodable A and B instances in the scope. So I can now decode my payload. And this thing now has type A. I don't know what type A is, but I know that this thing is of type A. And I also know that handler is a function from A to I/O of B. So I know that result is now of type B. Again, don't know what type B is, but I know that it's a thing that exists. Finally, I know that I can encode my type B back into a byte string, and I can send it back down on the wire. And so this is like a fully general server I've implemented right here, right? With some pretending like I have these functions. This thing 100% works. And that's pretty cool, right? Like, I have now provided a way that's type safe, but can handle whatever functions you want to throw at it, and I don't need to care. This thing is completely general for like any user code you want to put in. So that's, I think, the talk. Thanks for listening. Yeah, we didn't really get back to the monad question at the beginning, for which I apologize, but we can talk about it if anyone's interested. So that's what I got. Thank you.
So the monad thing. So the goal is to generate quick check tests for all the monads that exist in your code base, or what?
Yeah,
or just
I have a thing here. GitHub, leaking all my corporate secrets here.
This is being recorded.
That's fine. So I wrote this thing here. And essentially what you can say is, it's a little bit of template Haskell, because that's the only way you can reify instances. But you can say, get me all the dictionaries that are for the default class here. And so what this thing is it looks at every module that you've imported, and it finds every default instance, and then it gives you a list of existentialized some dict ones over default. And so this existential turns out to be existentializing the constraint and the dict that we looked at earlier. And so this thing is a proof of some dict, but we don't know what it is. And then this module also provides a thing called with some dict one, which is the eliminator for that. And so that gives you this proxy, which like is existential, but tells you what type you are using existentially. So now you have a reference to that type, and you can type check against it. And so I can say, like, give me a default value of type A. I don't know what it is, but I want that thing to not be undefined. And so what I've proven here is that like every instance in scope for default is not equal undefined. And so what this thing is this actually generates an H spec for each one of these things and will give me a test for every default instance in scope that they're not undefined.
Nice.
Yeah.
That's really cool.
Yeah, so that was the original idea of the talk, but I didn't want to have to like dive into the template Haskell stuff, which is super gnarly. And this actually turns out to be a big like graph search problem if you want to do it properly, because you can say, I have an instance of default as long as I have an instance of something else, right? And so you need to kind of traverse this big tree if you actually want to find all the instances. So the hack I decided was only pick the ones that are completely monomorphized, that don't have any type variables, and that works relatively well. The plan was like at work, we had a type class which defined like a state machine. And so those things were all only ever over a single type variable, and that was always monomorphized. And so we pull in all those things and like prove a bunch of things about the state machine that was like well behaved. That was kind of the original impetus behind this project. Any other questions?
Interesting. So like, you could basically use this sort of same technique for all of the monad like law checking that you.
Yeah, actually, so exactly. So if you wanted to do that with monad here, you'd replace this default with monad.
Right.
That would pull in every monad instance.
Got it.
And then here you'd say like,
You just change that.
yeah, you'd use the monad instances quick check thing.
Right. That's cool.
Yeah. So yeah, so it works all the way up to 8 type parameters if you really want to go that far. I've never seen a type class with that many, but you can do it. So, cool. All right, thanks for listening. I don't know how to stop.
You are done now.
I'm done.
Thank you for the talk. That was great.
Cheers.
Good time, I think.
Marvelous.
If you want to be even more object-oriented programming, you can include what